Hi everyone, welcome to the Hardware Software Co-Design for AGI Lecture 7, and in this lecture we'll be talking about GPU and CUDA programming. So we've already studied about AI models and their inferencing and what all operations is performed on it, and now is the time to actually learn about the hardware on which we're going to deploy it on. Our ultimate target is to reach FPGAs and MPSOCs, as we call them in modern languages, in order to effectively understand hardware software co-designing. But before we understand the FPGA's hardware software co-design, we'll reduce one variable in our designing methodology, and that is we'll reduce the hardware programmability. So now we have GPUs with us, which are completely programmed by the usage of software. So any proprietary piece of hardware which you see, whether it is a GPU or an FPGA or the CPUs, etc., all of them are actually intellectual property of the company which has made them. But in order to interact with the hardware, they need to provide a software support for it, and that is what is usually called as an SDK. So using the SDK, you can interact with the hardware which is developed by the company. And this is what we are going to study in this particular lecture about one of the particular software SDKs which is used to interact with NVIDIA GPUs. It is called CUDA. So from the perspective of a hardware engineer, hardware designer, hardware engineer, working on CUDA is at a very abstract level. For them, working with CUDA would be because they're so used to seeing RTLs and everything and embedded C programming, for them CUDA is a very high level thing. But from a perspective of a data scientist, CUDA is like a rock bottom thing. They cannot even expect to go below CUDA. Even if you tell them to write something in CUDA, they'll be like, oh, I cannot do this. So that is where the role, this particular lecture of hardware software co-designing, or this particular series of lecture I would say, come into the play, where we get the perspective of both how the data scientists feel like and how an RTL or hardware engineer feels like. And we are right in the middle to bridge the gap between understanding of a data scientist and a hardware engineer. So in this particular lecture, let me just bring out the highlighter. We'll delve into the utilization, how CUDA is utilized for training AI models on GPUs. We'll delve into the fundamental components of some contemporary computers and understand GPU's role in context of AI. We'll learn about the importance of understanding CUDA alongside the popular frameworks like PyTorch and how they inherently use CUDA in their lower layers. We'll have a detailed exploration into the composition of a modern computer, which consists of motherboard, CPU, RAM, GPU, etc. And the article will also set the stage for comprehensive overview of CUDA, shedding light on its pivotal role as a programming model that bridges the CPU and GPU to facilitate parallel math. And throughout the journey, fundamental programming concepts, CUDA kernels, launch configurations, communication between the host and device, the essential aspect of parallelizing CPU on the GPUs are explored, and this is what we'll be covering throughout this lecture. So, right, you can read the most of the paragraphs, like some of them are like more exploratory, giving you better explanations. Let's understand the significance of learning CUDA. So prior to delving into the extensive post, I would like to acknowledge a query that may be occupying the thoughts of numerous data scientists. What is the advantage of CUDA when PyTorch is already available? So as you might have already noticed in previous labs, that PyTorch is almost indispensable when it is coming to PyTorch or any more machine learning framework. The usage of it enables like cutting edge research and a very easy way to develop models, do the training, testing and performance enhancement optimization, but because of their user friendly nature and their computation capabilities. But however, PyTorch may not always be sufficient when it comes to the latest AI developments. And for example, there is an example of flash attention. So attention is all you need was a paper, and there is a modification of it called flash attention. We'll discuss into the transformers, attention layers, self-attention layers somewhat into the last part of the course, and during that time you'll be able to appreciate this more. But we won't be going into the CUDA level of development in it, but the implementation of flash attention on PyTorch of attention in CUDA increases speed by 10x. And as always, I'm saying this, we're not in this particular lecture not talking about flash attentions, but rather discussing a broader trend. So the evidence is unequivocal. The larger models are superior, and AI models can achieve great size and usefulness as their training and serving processes grow more efficient. And PyTorch plays a crucial role in advancing the current level of technology, but low-level CUDA is still necessary for efficient implementing state-of-the-art AI. Certain functions like sparse matrix multiplication, as we had seen. So PyTorch inherently utilizes it. But if there is a modern architecture of GPU, let's say the H100, which introduces more level of sparsity, like a better way of multiplying sparse matrices, and PyTorch has not implemented that, so you can use CUDA to take the advantage of that technology. And as I've said, PyTorch employs CUDA, and to connect like whatever computations you're typing on PyTorch to ultimately put it on GPU, CUDA is the gateway for that. So you're already using CUDA in one sense, and therefore it is important and significant to learn CUDA alongside PyTorch. So let's understand the composition of a modern computer, and 99% of computer is composed of the following elements. Like there'll be few of the other elements which you might have besides this. We have the auxiliary components like power supply, the cooling unit, and then the main components like the motherboard along with the storage space. Inside the motherboard we have a CPU, RAM, and an onboard storage and a GPU. So for the purpose of this article, we are chiefly interested in understanding the motherboard, the CPU, RAM, and the GPU. So motherboard is the backbone of the computer. Like I'm just beginning from very basics and having certain illustrations to get things in the right context for all of us, and we feel all in the same platform, that it's not a very high level concept which we're discussing. It's all like something which you're practically using in your day-to-day life. So this is your motherboard, which connects all the components together, and in the middle of the motherboard lies the beating heart of virtually every modern computer, the CPU. And the CPU is responsible for executing calculations necessary to run a program, and is one of the most important components of a computer. So you can see a CPU which is generally covered by a cooling unit, a fan or heat sink. Because the CPU produces heat, the CPU is typically covered with a heat sink, and inside that, this is how it looks like. This is an image of an Intel Xeon processor. Xeon is a server grade processor of Intel. And very close to the CPU is the RAM, which stands for random access memory. RAM is the working memory of the CPU and is designed to allow for the rapid access of relevant information. So you can see RAM. Another popular component of computer is the GPU, and we'll get into exactly what the GPU does in the following sections, but for now it's sufficient to know that GPU is designed to help CPU on certain type of calculations. PCIe or Peripheral Component Interconnect Express, PCIe Express, is a set of ports on many motherboards which allows the CPU to communicate with external devices. And the most common use of PCIe is the connection of GPUs. But PCIe is a flexible interface. Many times your LAN card is also coming through, like if it's a very high speed LAN card, the information is coming through the PCIe port, which allows storage devices, specialized cards and other devices to be connected to the computer. In many ways, components on the PCIe bus are add-ons to the core of the computer. The CPU and RAM are vital in the operation of the computer, while devices like GPU are like tools which the CPU can activate to do certain things. This conceptualization remains relevant even at the lowest levels of programming. Thus, often the CPU and RAM are referred to as the host, while the GPU is referred to as a device. Now, it's a very important thing, a very sometimes you will just use the words like host or the device, but you have to be clear with it. Even when you're using FPGA, what we are referring to as host and what we are referring to as the target board or the device. the CPU and RAM are referred to as the host, while the GPU is referred to as the device. This is a standard convention we follow. So the host you can see in this, and the device, the GPU, which is attached to the PCI Express port. So structurally, if we remove the outer casing of the GPU and examine its inner working, we'll find that GPU is somewhat similar to the host. And it also has the graphic card, which is the complete thing. Inside that we have a layers of silicon which we fabricate, the GPU. And many companies like SUs and other companies like MSI, and I'm just remembering these two names as of now. They manufacture the card, but the GPU, the main GPU which they use inside is by NVIDIA. And NVIDIA mainly does not lead to the board, the manufacturing of the graphic card. They only, they majorly deal in, they have certain NVIDIA's graphic cards as well, but mostly they deal with GPUs, and other companies purchase this GPU and make a graphic card out of it. So if we examine the underhood of what is inside this, so we'll see that there is this GPU part and the VRAM part. So there are other major components of the graphic card beside the GPU, like VRAM, which is essentially the graphic card's equivalent of the CPU's RAM. And thus we come to the major conclusion of this section, that the device, the graphic card, has a processing unit and memory, same as the host, which has a processing unit and a memory. Both the device and host have the necessary resources to work independently from one another, and building low-level applications which uses both the device and host requires programming two entities which work collaboratively. So natural question which might arise at this point is, if the device and the host are so similar, just a compute model and some memory, why do we need both of them? So now we'll understand why the architecture of GPUs actually enhances the performance in AI calculations or doing certain kind of calculations which the CPU somehow becomes bottleneck or thresholded at. So to understand why the GPU exists, it's helpful to first understand the CPU a bit more thoroughly. The CPU is made up of cores. A core is a circuit designed to do basic mathematical operations very quickly. While the math a core can do is fundamental, and combining many of these simple calculations can result in virtually any mathematical operation imaginable. A modern CPU has several of these cores such that the CPU can work on multiple things simultaneously. And the CPU has different type of memories called cache, which is designed to speed up the CPU and also to communicate information between the different cores. So here you can see the structure. There are 4 cores which you can see, and an L1 cache, L1 cache, L1 cache attached to each core, and there is this L2 cache combined for a pack of 2 cores, and then there is an L3 cache for the entire 4 cores together. The CPU has different type of memory called cache, which is designed to speed up the CPU, and the whole idea of the CPU is to run a program which can be conceptualized as a list of operations, and it wants to do it as quickly as possible. While a CPU can do things in parallel called multi-threading, the main focus of the CPU is to be fast as fast as possible in back-to-back calculations. Thus, each core of CPU is designed to do each operation as quickly as possible. And this approach is vital for many applications. Some calculations simply need to be done one after the other, and the only way to do these calculations faster is to make each step as fast as possible. However, some applications can be parallelized. So you can see that in this diagram, if the task 2 depends on task 1, then the CPU is a better target for doing this, because it can achieve the task 1 in a much better way than as compared to a GPU, and it can quickly switch over its context to the information which has got from task 1 to task 2. The idea of the GPU is not to optimize single calculations, but to optimize running many calculations in bulk. Generally, the GPU is much slower than the CPU at a given calculation, and thus only really shines when there are sufficient calculations which can be run in parallel. When applied to the right problem, the GPU can be 100x or even 1000x faster than a CPU. So there are 2 core deviations that GPU takes from the CPU in focusing on parallel computation. First, the GPU has a greater quantity of cores than the CPU, which you can see in this diagram here. But those cores are less capable. This means GPU can do more calculations at once, but those calculations are typically slower. The GPU is set to allow for single instruction, multiple data. Basically a single control circuit, multiple cores within the GPU. So lots of data coming in, but all of them are having the same instruction which is to be performed on them. At that, the GPU outshines. So you can see the kind of a structure which the GPU follows. It has many cores and an L1 cache and a control unit attached to the whole row, along with an L2 cache for the entire thing. So originally the GPU was created for rendering graphics for video games, but has since exploded in popularity, consequently exploding Nvidia's valuation, which you can see how it has raised from the AI boom which came, or actually the AI and blockchain boom together, which came in around 2015-2016 time frame. So as it turns out that there is a lot more other useful things rather than just playing video games which GPUs can do. And AI models, for instance, are a perfect use case for GPUs, as AI is basically done with a bunch of simple and more or less independent calculations. So if there is a stream of data which is coming in and all these points are independent of each other, and you have to add them all and multiply them by 3. So if you just look at this particular layer, how many operations do you see in total? So there are 25 of these, and first you add them all and multiply them by 3, then you multiply them by 2, then you multiply them by minus 0.1, you wait for all the results, and then you have the operations here, which again you turn to add all of them together here. So 25 and then multiplying by 3, 26, 27, 28, 29, 30, 31. So if there are total 31 operations, and theoretically if you can just somehow or the other break them into parallelized steps, which you can do, and it turns out that you can break up into 9 parallel steps these operations. So in theory itself you can run the whole model 2.4 times faster if you can break it into 9 parallel steps. And real AI models can see up to 100x, 1000x or even higher speeds when the amount of data is even larger. So we understand the core components of the computer and we understand that why GPU is useful in AI. Let's start getting an idea of how to get the GPU to do things. So as with any, in the starting, as we had a discussion about how to utilize any hardware, so there is an SDK for it, and where to run that SDK, and every hardware or every processing unit comes with its own instruction set architecture. And what a compiler essentially does is that whenever you write a code in a high level language, a compiler will break it down into the instruction set architecture of the platform which it is going to be run on. So what CUDA stands for is a Compute Unified Device Architecture, and it is NVIDIA's parallel computing platform. And CUDA is essentially a set of tools for building applications which run on the CPU, but they can interface with the GPU to do parallel math. So whatever you compile with the NVIDIA's CUDA compiler, what it will do is that it can use both the host and the device. So whatever things you want to send to the device, it has instruction set architecture for doing that, and whatever things you want to run on the host, it has certain constructs which like the instructions which it can use for compiling on that processor itself. And probably the most popular modern language to run CUDA is C++, and that's what we'll be using. And you don't have to worry about whether I know C or C++. The approach we'll be using will be very, it's very straightforward. So I think everyone can approach it. And it is good also to get an idea of this kind of C code we'll be using in this, because embedded C is a very popular thing for coding or developing on most of the boards, including the STM boards, and it's a very famous high-level language for interacting with your hardware. So I'll be using Google Colab as my development environment, and there is a handy Jupyter extension that can compile and run CUDA code just like if it was a normal code block. And this allows Jupyter to hook into NVCC. NVCC is NVIDIA's CUDA compiler, and luckily Google Colab has already NVCC set up for us, so we just need to install and load the extension. If you click this link, it will take you to this notebook, and you can start executing this notebook. Before you do that, you just have to ensure that you are connected to a host time. You can change runtime type if it is not connected to GPU already to a T4 GPU for you, and you can create a copy for yourself if you have to make any changes. So we waited for it to get connected, and we have certain 12 GB of RAM, GPU RAM, and the disk space available with us. So these are the resources. We can run the Jupyter notebook. First of all, we'll install the NVCC for Jupyter. After it has successfully installed, we load that extension. Once that extension is loaded, we can actually start running the CUDA code, the CUDA C code with header of %% CUDA. So this indicates that it is a CUDA code which we are trying to run. So we'll understand that each of what this global context is and what this block IDX and thread IDX are. So let's go back to the article page. So this is what we've just seen, that we can run a block of CUDA code just like a normal Python block by adding CUDA at the top of the cell, and we just try to run this whole code. Now comes the discussion of what are CUDA kernels and launch configurations. So kernel in general are the core component of an operating system, and kernel is what manages system resources and communication between hardware and software components. The kernel is responsible for tasks such as process management, memory management, device management, and all the system calls. So the CUDA kernel also does the same thing. It does the same thing for the GPU. It is the core component for actually managing the resources of the GPU and enabling the communication between the GPU, which we're calling as the hardware, and the host. And it is responsible for tasks such as process management, memory management, device management. You'll see that, and even the mathematics we'll do, everything it is responsible for is CUDA kernel. So in the context of CUDA kernel is a function written in C, C++ that runs on the GPU, and CUDA kernels are executed in parallel by multiple threads on the GPU. The more on this coming shortly, that what are these threads, and because it can parallelly execute multiple threads, it allows for massive parallel processing, which is ideal for computationally intensive tasks. So in CUDA, we define a kernel with the global keyword before a function, and we can also run the code on the CPU with the host keyword. So as we ran the first program, here you can see that %% CUDA, and we just include the standard IO of the C program. Because we've defined __ global this keyword here, and after that we've written the function void hello and done the printing statement and given the block IDX and thread IDX. So this part of the code will run on the GPU, and this runs on the CPU because it's defined as host. So host, which is running on the main CPU, is calling this function, and 2,2 it is passing. So let us understand that what are these two parameters here. So because this is a C++, the first thing that gets executed is the main function, which happens to be on the CPU or the host. And then on the CPU, the first line of code that gets called is this line, which we saw, hello, followed by 3 these angular brackets passing 2,2 inside it. So this is called a launch configuration, and this launches a CUDA kernel hello on the GPU. In CUDA, a parallel job is organized into threads, where a thread is a piece of a program that can work in parallel. You can spool up multiple threads on a GPU, and they can all work together to do some tasks. So if there's a task, you can break the task into multiple threads, and each of these threads will run independently to do that task. So this is known as task partitioning. These threads exist in something called as a thread block. So on modern GPUs, there can be 1024 up to 2^10 threads per thread block, and threads is the same thread block share the same address space in the VRAM. So anytime any of these threads inside this whole thread block, they will share the same address space in the VRAM. So they're able to work with one another collaboratively on the same data. Like if any of these threads is wanting to access the data, So it will access it from the shared memory which they have. So while you can have up to 1024 threads per block, you can have tons of thread blocks queued up on the GPU, and each of these blocks will share the same address space in the VRAM. So most GPUs have the resources to execute more than one thread block at a time, and one GPU might be able to execute two thread blocks at a time. So one GPU might be able to execute two thread blocks at a time, another might be able to execute 8 of them. So this means the same CUDA code can leverage both large and small GPUs. So smaller GPUs can just have two thread blocks running in parallel, and larger GPUs can have up to 8 or 16 or any number of thread blocks running on them. But the same CUDA code can leverage all of them together. So we define how many threads and thread blocks we'll be using with our launch configuration. So within the triple angular brackets, we specify the number of thread blocks as the first parameter and the number of threads per block as the second. So here, if you're mentioning 3 and 2 here, so what we are actually meaning is launching out kernel across 3 thread blocks. So this first parameter here is the thread block, each consisting of 2 threads, which is the second thing here. So block ID X refers to the block ID and the thread ID refers to the thread ID. So it is directly picked up from here. So if you see that if we pass 3, then the block ID can go from 0 up to 2, 0, 1, 2, and the thread, if you are passing 2 here, can take two values, 0 or 1. And because all of these are being executed in parallel, so there is no guarantee which one will conclude first and get printed. So the kernel is running on the GPU, and to get the results from printing back onto the CPU, so it can be displayed in Jupyter, we are using the CUDA device synchronize to wait for all the threads on the GPU to complete. And this CUDA device synchronize allows the printouts to propagate from the device to the host. So when you run a kernel, CUDA automatically creates some handy variables, and two important ones as we saw are block IDX and thread IDX. And you can use these two variables to understand which block and which thread is currently being run. Thread blocks can organize threads in up to 3 dimensions, and blocks themselves can be organized in up to 3 dimensions, meaning block IDX and thread IDX can have X, Y and Z attribute. So this is why we are actually how is this architecture to have 3 dimensions is because you want to do multiple matrix operations or any operations in parallel, and for easier management of block IDs and thread IDs, we have these attributes with us. So if we define the dimensions of the grid and the block, let's say as grid dimension 2, 2, 2, and then we define another dimension for the block as passing again 2, 2, 2. So block dimension is the grid of threads per block, and this grid dim is the number of blocks itself. And if you launch this in the configuration, and for everything we're printing the block and the thread, so you can see that there are multiple blocks now, but each of these blocks can be accessed like separately. They can be accessed, and inside each of these blocks there can be multiple threads. So all this is for actually doing the parallel computation tasks and managing that efficiently. So in other words, CUDA allows you to build a grid of calculations in up to 3 dimensions and inform a thread where it is in that grid via the block IDX and thread IDX, which is having the 3 attributes of X, Y and Z component. Now comes the important idea of the communication between the host and the device. So just like in our normal C program codes, we use malloc function to create memory in the heap memory. Similarly here, in order to reserve some spot on the VRAM, we use the CUDA malloc function. Then you use the CUDA memcopy function to copy data between RAM and VRAM, and when we're done on the GPU, we can use CUDA free to let the GPU know that we don't need the data in VRAM anymore related to that block and threads. So after data has been sent to VRAM, we can run a kernel on that data, then copy the result back onto the RAM effectively using the GPU to do all the parallel math operations. So let's explore a very basic idea in this code where we send two values to the GPU and use the GPU to add those numbers together and get the result back into the RAM and print the result. You can actually like run this code here as well, whatever we have discussed till now, and the whole idea, you can see that everything will get displayed as it is what we had discussed. This thing we'll tackle later on, the CUDA library. We're discussing right now the communication between the host and the device. Alright, so while I am explaining this, you can follow along this. In the end of it, we'll do a very simple math operation in this. So this is how the code is looking like, and we are defining a function called add_int CUDA, and they are pointers to two integers, and we're just simply doing the add operation, and this add operation, where it is actually happening is in the GPU itself. By this global function we are doing this. So the instruction set architecture, when we compile this whole code using the NVCC or any compiler which we're the NVIDIA compiler which we're choosing, because this global keyword is there, so it will render this operation into the instruction set architecture of the GPU. So running main on the host, which triggers the kernel. So we have a more graphical representation of this, but first just let's look at the code at a high level once, and then we'll come back to the code again. So we are defining the values here, and we're printing the expression, but we're not printing what is coming after that. We're just printing the expression, initial expression as of now. Then we're creating device pointers for the GPU, allocating memory on the device of the GPU, and copying values from the host to the device GPU, calling the kernel to add two values pointed by these memory locations, and finally we are doing the copying back the results back to the host, and then printing the result and freeing up the memory. This is what we are doing. And here we have a more graphical representation of how the RAM and the VRAM come into the play. I can understand that some of you might not be very comfortable with C++, and therefore, as I promised, we'll be not having very fancy C++ things coming up. But very basic thing of it is the star and the and, probably a star and the and operator. So these have to do with the pointers. So when you run the code int a is equal to 1 and b equal to 2, it gets triggered on the CPU, and two spots in the RAM get allocated to store the values. So let's say that address 4 and address 8 is occupied for that. So each of these values have some address, which you can see is written by address 4 and address 8. So it generally how we refer to in terms of hardware engineering, hardware level engineering, is that we have a base pointer which is pointing to this address space, and then we do a offset of that, and you might have done this kind of a calculation in your microprocessing and interfacing course in undergraduate level or some or the other course, right? Base pointer plus the offset of it. So that gives you the address of where it is stored in the RAM. So each of these values have some address, and when we call AND A or AND ampersand operator B, we are getting the address of those values and not the values themselves. So in order to capture where this A is stored, we can do ampersand A operation. So if you want to keep track of an address as a variable, you can create something which is called a pointer. So pointer is nothing in C but a variable which stores the address of another variable. So variables in themselves can be 2 bytes long, 4 bytes long, 16 bytes long, depending on whether they are int, unsigned int, float, the precision of the float like 16-bit or 32-bit. So the variables in themselves can be long, but the address of them will be all like 2 bytes each. So pointed to different different data types, the pointer will be to the address, and address of a one single type, which is of having just 2 bytes or 4 bytes. So if you want to keep track of an address as a variable, you can create something called a pointer. A pointer is a data in memory that points to some other data in memory, and if we run the code int star pointer to A with ampersand A if we pass, we would create a spot in memory which holds a spot in which, again it's complicated, you can like pause and read, but simply if we create pointer to A by passing this sort of a code here like star DA, then it is creating a pointer in the memory, and we can point that to, by using ampersand A, we can point that to the address of A. So this idea of pointing to data in memory is critical in low level computation and thus is critical in CUDA because we are dealing with two independent systems, the device and the host. We typically create pointers which point between the two memory spaces. So in this example, we create our integers. After we create our integers, we create two pointers which we are calling as DA and DB, and to signify their pointers, we are putting this this asterisk operator in front of them. So these are pointers on the CPU's RAM which initially don't have a value, but their names with D underscore, signifying that pointers will be used to store the location of the data on the GPU's VRAM. As of now, at the time of initialization, since this whole code is running on the host, therefore they are created with null pointer on the CPU's RAM. At this point, we call the CUDA malloc function, which is designed to allocate some spot in the GPU's VRAM. So as soon as we call CUDA malloc and we pass in this size of like how much space you want to reserve, this will return an address, and we'll capture that address in the pointer which we have made in the RAM. So the VRAM's address is captured in the RAM's address space. So this diagram is making this clear, that how in order to actually use these locations in memory, the host needs to know about them. That's why we pass ampersand D and ampersand DB into CUDA malloc. We are telling CUDA malloc where to store the new VRAM's allocation on RAM. So here by passing CUDA malloc DB, you say that the DB will hold the address 2 and CUDA malloc DA will hold the address 5. So inside the address 10 of the RAM, there is address 5 stored on the VRAM. So this is how we are actually referencing the VRAM. So now we can copy the values of A and B to VRAM using the following code. So using CUDA mem copy, we can specify like which address we want to copy to, which is stored in DA, the value which we want to copy to, and the size of this. And by calling this CUDA mem copy host to device, we're doing this CUDA mem copy. Later on, you will see that again we'll do, after we do the kernel operation of AND, we'll again do the mem copy, and this time we'll copy the value of DA. We'll copy what is stored in DA and in this address which is stored in DA, and we'll put it into the variable A. And we'll use CUDA mem device to host. So before we was using host to device, now we'll use device to host. So then we launch a kernel. We can pass the kernel D and DB so that the kernel knows which values on VRAM need to be modified. And since here we are passing what is D and DB is actually the address. So here what we are capturing is the address, like the pointers A and B. And if you're capturing the pointers A and B, so just by referencing A0 and B0 here, we're actually referencing the data. So this is somewhat little tricky. People get confused when to use the pointer, when to use the normal variable. That is something which you have to study and spend time and get little practiced on in order to utilize it, but it's a very standard thing. So after we've done A0 at the whatever is pointed by the A, add that with B and again store that back in A. So if it was 1 and 2 initially, 2 and 1 here if it was, then whatever is there in B will get added to A and will be stored here. So it will become 2, 3. So the value which DA points to get copied back onto RAM and then its value is printed, and thus printing the final result by using this operation here. So the GPU doesn't know that CPU is like, nearing the end of its program, and it no more requires the blocks and the threads which it was working upon. So the value on the GPU will sit there until the application finishes. So for this small problem, this doesn't matter. But if you had about 1 or 2 billion times, you might want to want a billion ones and twos taking up space on your VRAM. So if there are many data points, then you would want to free them. So you free them by calling the CUDA free, and you free those address spaces which you had previously occupied. So obviously this is not the most effective way to add two numbers together, but I hope it gives you an idea that how data is passed back and forth between RAM and VRAM, and this is something which we wanted to understand. Before we dig up into building AI models from scratch, I think it might be more useful to go over slightly more advanced examples so you can really feel some level of mastery at CUDA. So just like the C++ compiler which we passed, like C++, we can use NVIDIA's CUDA compiler NVCC to control the compilation process, and you can pass on all the files which you want to compile together and can build a single binary out of it. It has various command line options to optimize and control the behavior of your CUDA code compilation, and a detailed list can be found here. So this is the documentation, and in ECC you can specify that the direction, you can specify the verbosity, the output file name, and the include paths, like which all paths you want to include, which all directories you want to include while you're doing the compilation process. So it will reference all the code from there as well, and these are certain directives which you can use. So we'll actually, in order to work with CUDA more, we'll use NVIDIA's CURAND library for generating random numbers. Now there are multiple libraries in CUDA, and in a moment we'll see, but first of all let's see that if you want to compile with the with this CURAND library, so that's we generally call it CURAND, or if there is a BLAS operation like basic linear algebra subprograms, that's what BLAS stands for. So we'll call it CUBLAS. There are multiple CU libraries, and many major, like all the important companies which make hardware like NVIDIA, Intel, AMD, all of them have their own implementation of certain libraries, like generating random numbers, doing some linear algebra, doing some graph operations, doing some deep neural network stuff, etc. They have their own implementations of their library, and in a minute I'll show you a table which compiles all of them. So let's first of all see that how this program works. So this program uses the host CURAND API to generate 100 pseudo random float numbers, and in this directive we are passing the CURAND, and we are also including that in the header file. So we are defining two functions to help us figure out any error. If any error occurs, we will simply put an exit, like error at what file and line we are having, and we'll just simply fail. But anytime we have to do any CUDA call or CURAND call, we'll use these two functions. So the idea here is simple. We'll just use the calloc function to allocate n floats on the host, and then we'll use CUDA malloc to allocate n floats on the device. Then we create pseudo random number generator by calling a CURAND call, and we'll use this CURAND create generator, and we'll create pseudo random number generator using this line. Setting up of seed is sometimes important in order to replicate the result, so we'll set up the seed by using this CURAND set pseudo random number generator seed, and then finally using the CURAND generate uniform, we'll generate the n floats on the GPU, and then by using the CUDA mem copy, we're just encapsulating all this inside CUDA call, current call, because if error happens at any stage, we want to know that what is the thing which has thrown the error, which line has thrown the error. So that's why we're encapsulating, like we're putting this inside this whole thing. And then finally, after we've copied from device to host into the host data, the n allocates which we have done before, after we have done that from the device data, we'll just simply display the results in up to 4 precision values. So you can see that, and after that we'll just clean up the whole thing. So this is what you should get as an output. So to read more about this CURAN library which we have just used, it's best to explore the documentation of it. So you can go over to the docs.nvidia.com, and I'll just help you explore that what all APIs and documentations they have for different CUDA libraries which are there. So there are certain CUDA math libraries, and if you go inside the NVIDIA CUDA, so this is the complete documentation of all what NVIDIA has to offer, like their enterprise related AI stuff and the deep neural network accelerator, the NVIDIA Jetson, TensorRT, Omniverse. All these are different products and SDKs by NVIDIA. And inside the CUDA math libraries, you'll see the CURAN library. And as I was mentioning before, that there is a fast Fourier transform library which is very much used in signal processing. There is CUSparse library which is for doing the sparse matrix multiplications that we had discussed. There is a CUSolver library for solving differential equations, a CUBLAS library for solving all the linear algebra type of programs. And in anything, if you go inside any documentation, you will see that how to call that on the host. So there will be a host API overview, and we have simply followed that to make this program work. So at this time, you can attempt a task on your own, which will be part of your lab exercise, and you can use this compiler to compile your code. Include the necessary header files, define a kernel function, and define a kernel function to generate uniform random numbers using the CURAN library. And in the main function, what you have to do, allocate memory on the device for the current state and result array, call the setup kernel, call the generate kernel, and copy the results back from device to host, print the random numbers on the host, and fill the allocated memory. So this is the task which you have to attempt. Parallelizing a CPU program on the GPU. So we have 2 subtopics remaining for this lecture, about parallelizing a CPU program on the GPU and about using NVIDIA's profiler tool for seeing which are the most memory consuming tasks which we are running. So in the previous section we went over how to launch a kernel and how to transfer data between the host and the device. And let's use those concepts to parallelize the program written for the CPU, and this will inherently give you an entrance into accelerating or parallelizing programs for running your AI models, which your AI models will run on. So below is a brute force implementation which attempts for each 3D point in a set of points to find the closest other point. The end result should be a list where the value in the ith spot is the list. In the list should be the index of the point which the I point is closest to. So if there are 3 points, let's say 1, 2 and 3, and the first point is closest to point 3, then instead of in the return list it should print 3 here. And if point 2 is closest to point 3, so this at the second index it should again mention 3, and if the point 3 is closest to point 2, it should mention 2 here. So that's what we want to find out, and here is the implementation of the CPU. Now all these tasks, if you had to do in CPU, you would run a for loop and would try to actually do that. But we'll see how to parallelize this whole task using a GPU. But first let's see the implementation of the CPU. I won't delve into the algorithm much, but we can figure out the algorithm itself. It's just like comparing the distance between of each point with every other point. So the algorithm we'll use here is very simple. So let's first of all, before finding closest point in the CPU, Before going through this algorithm, let's just look at the main function once. So we are defining 10,000 points. We are defining a variable count, and we are defining pointers to the to store the index of the closest one, and we are again initializing that by 10,000, and we are getting 10,000 points. And in each point we are storing, we're using a random number generator. We're storing a point here, and now what we're doing is we're calling this function. We're wanting to time it actually. So before we start this call, we're noting the clock time and storing it in start, and then at the end we're again subtracting it and dividing it by clocks per second to get the total duration, and we're printing that duration. For the algorithm in itself, what we're doing is we're taking in the points and the indices and the count, and if there's a base case, like if there is just count is 1, like then we don't do anything, we just return as it is. But for if there's, then we create a loop to go through every point, and we call this variable as the current pointer, and the current pointer should be less than the count, and every time we are increasing the current pointer. So when it is at the first place, we try to compare that points distance to every other point. And as I said, this is not like the most effective implementation, but there can be many more sorting techniques and certain things which you can figure out, but we're working with the most naive solution. And distance to the closest point, so we're setting the largest float value to the whatever is possible, and then we're increasing the count to check the current point with all the other points, and we're calculating the Euclidean distance between the current point and the point which we're currently going over through, like all the other points. And we are choosing their x coordinate, y coordinate and z coordinate, like x square plus x2 minus x1 square plus y2 minus y1 square plus z2 minus z1 square. So this is the distance square, and we are comparing that with the distance to the closest. So if that is true, we are storing the current pointer's index as that value I, whichever satisfies this relationship, like whichever one is the closest to it. And if we time this, then you'll see the test 0 took 1.28 seconds, test 1 took 1.22 seconds. So this is how we're we're doing 10 tests on this. You'll see that sometimes doing the same operation, CPU took 1.2 seconds, and sometimes it took up to as long as 1.8 seconds. So to parallelize this code on the GPU, we need to get points on the VRAM and then launch find closest on the GPU as a kernel. So this is the parallelized version on the GPU, and let's walk through this thing. Again, we're defining this global function here, and this time find closest GPU will run on the GPU instead of running it on the CPU. And broadly, we'll again look at this function later on, but let's just first of all look at the main function. I've broken down these steps in individual parts in the later part of the, in the next, after this code. But broadly, we're defining the parameters, we're defining the random points, we're defining again the device pointers, allocating memory on the device. We're copying values from the host to the device, and then launching the kernel, and then freeing the device memory. And before we look into that code, let's just look at the result once. So you see that by parallelizing this on the GPU, the timing reduced more than 100 times. So the approach starts off with the same as the CPU approach. You create a bunch of random numbers, and that we need to sort. So that's how we create the random points in a similar way. Then we allocate some space on VRAM for the points as well as place to store our values. So by using CUDA malloc, we do that, and size of int into count. So this is the total space we would need to store the index, and this is the total space you would need to store the points. As I told you that this is the pointer in itself, and therefore it just requires the size of an integer, but these are the points, and therefore we require float 3. We copy the points from RAM to VRAM by using this CUDA mem copy, and these are the host points and these are the device points, and this is the number of things which you have to copy, and copy CUDA mem copy host to device. And then we finally launch the kernel. So how we launch the kernel is something which we need to look into. But before we get into this find closest GPU, we first of all look at the arguments which we are passing. So here we are accepting the points, the pointer to all the points which we have of type float 3. So these points we are passing, and we are also passing the indices where we will store the index of the closest, and finally the number of count, the total number of points which we have. So here the code will broadly look the same. So before that, like, what is the configuration which we are choosing, the launch configuration? So we've defined a variable called threads per block, and we're choosing 64 threads per block, and the number of blocks in themselves which we're choosing are divided by, like, the number of blocks is count divided by threads per block plus 1. So this plus 1 would convert it into an integer, not to a floating point. So we have a round figure for both of them. This value would be, if the count is 10,000, this would be around 150 or so. And you can calculate that calculation in itself is not very important. So brute force implementation of this is that we'll first of all calculate the IDX by adding this thread ID, block ID and the block dimension. So before we were trying to actually do this loop kind of an operation, that the outside loop which we had seen, this loop for current pointer equal to 0 to current pointer less than count. In this we have ensured that the number of for each thread which we are having, we are calculating the IDX. So we are adding the thread ID, the block ID and block dimension, and this ID is less than count, it means it's a valid thing, and we'll continue. If it is not, if it is coming more than the count, then we'll just simply do nothing in that thread. That thread would start and end as it is, like, nothing to perform. But if the ID is less than the count, what we'll do, that we'll pick up that count from, like, whatever this IDX comes to, we'll pick up that point and we'll compare that point with all the other points. So this, we are referring to this point as the, out of 10,000 points, we are referring to this point as the points IDX, and we are defining the smallest so far as the largest value of float which is possible. So it's a brute force implementation. Instead of, like, if you're getting confused, you should pause and just read this article, it will give you much clarity. And we're calculating again the distance squared, and we're storing that. So now for each thread we are doing this operation, and naturally by doing the parallelization we are able to solve this problem in approx 100 or 1000 times much more effectively. So this is what is mentioned here. We can assign each thread as an individual point specified by as IDX, and we can do that by essentially counting which thread is currently being executed out of all the thread blocks. And each of these thread ID, block ID and block dimension combined will give you a unique point, and if that is less than, like, whatever the count value is, you will do that operation inside that block. And finally you will copy the values back, and just like that we've done some honest to goodness work on the GPU, and we're almost ready to get into building AI models from scratch, and that's part of one of the lab sessions which you're having. But before that, we'll just cover one super important topic, which is the NVIDIA profiler. So when implementing complex parallelized programs on CUDA, it's useful to know what types of operations have the largest impact on performance, and that's how we want to profile our code. That's where the word profiler is coming from. So instead of calling %% CUDA at the top of our code, we can do like write file find closest gpu.cu. So cu specifies the GPU C code, like which can be compiled by NVCC to write out CUDA blocks to as a text file. So you can see that like the same file which I had before. In that you like, let me just open the notebook. So here is the parallelizing CPU task on GPU. You see here at this point you see that we have written write file, find closest GPU to CU. So what this does is it compiles this and writes find closest GPU.cu code. Then we can compile this because we already have NVCC installed in this, so we have CUDA compiler installed in this, so we can compile this using this kind of a directive. The output file name will be find closest GPU.out, and the input file that we are using for compiling is find closest GPU.cu. And then when we run this profiler tool / find closest GPU.out, you will see that obviously the whole code will run, and it will also profile it. So you can see that there are multiple columns in this which shows GPU activities and the API calls, how much time it took in milliseconds, and as percentage wise the number of calls which were made, and average, minimum, maximum, and the name of that. So you see that total 10 calls were made, and so the average is simply 2.3819 milliseconds per call. And this was the call to the find closest GPU. So this was the thing which was having the highest memory consumption and the time consumption. And rest simple, like mem copy and device to host and host to device took like just 0.19 and 0.05%. In terms of the API calls, which took most of the time, was the CUDA malloc. In order to allocate that memory, it took around 188.75 milliseconds. And the CUDA device synchronized to wait for all those things, it took around 23.2859 milliseconds. And CUDA mem copy and how much each of these things were taking the time in nanoseconds or microseconds or milliseconds, that is mentioned here. So this is your NVIDIA profiler tool, and as can be seen, doing stuff with memory took over 99.19% of the time of this application. We won't get into optimization in this lecture, but generally when doing CUDA programming, the majority of time is spent optimizing memory and inter-device communication rather than on computation. And that's how the initial program, the initial example which I gave you, flash attention, it achieved the speed up of cutting edge AI by 10x by optimizing this memory copying and memory utilizations and everything. So that's it for this video. Thank you so much for listening to this.